everybody. Welcome to Cooking is Practical Chemistry. Our topic today, cooking includes such chemistry activities as experimental measurement, time of water boiling, solubility, mixing water with salt, sugar, or oil, heat capacity, heating salt, sugar, butter, and water, combustion calculations, and colligative properties, I don't know that word.
Can you spell it?
Yeah,
it's right
it's spelled right through.
Oh, yeah. I don't know, either way, it looks like coagulation, which makes sense. We had some discussion pre-con, and we came up with 3 topics that we can info dump at you. We're going to do that for about 15 minutes each on each topic, and then we will have time for questions. Our first topic will be extracts and fermentation. For example, how do we get from ingredients like coffee beans, dandelions, and cabbage to cappuccinos, wine, and kimchi? How do these processes change the ingredients on a chemical level? Our second topic will be cooking and baking. What happens when we apply heat to stuff? How does bread even work? And part 3, humans and food have good chemistry. What's going in our mouth and guts when outside chemicals, aka food, meet the human body and its systems?
Inside chemicals.
So, would you please raise your hand if you have an open seat next to you? We are not standing room only yet. Come take seats.
Yeah, we
really
actually need to have butts and
Yeah.
seats.
I'm glad everybody came.
Yeah. I sent out a...
I will answer that for you. So would you hold that up nice and high so everyone can see, please?
there's
These
a
are
big one over here.
handy-dandy question identifiers. So if I want to say, if someone is raising their hand, Renee, could you hold that back up, please? If I don't know your name, like my friend in the front row, I can say, hey, person with the red X, it's your turn to ask your question. Yeah, so when we get to that portion of the panel, we will ask you to please use those.
I got 2
There are 2
seats down
seats in the
front,
front row.
and there's 1 seat over here.
Okay.
All right, so let's get talking about extracts and fermentation. How do we get from ingredients like coffee beans, dandelions, and cabbage to cappuccinos, wine, and kimchi? How do these processes change the ingredients on a chemical level?
Should we introduce ourselves?
We should introduce ourselves. How about you start, Kurt?
How about I start? Okay, I see a couple friendly faces here from the last panel, but if you don't know me, my name is Dr. Kurt Fleschner. I'm a practicing podiatrist and foot and ankle surgeon in the Sacramento, California area where I am currently in private practice. I focus on limb salvage, wound healing, and limb reconstruction. And I'm a current instructor of orthopedics for the Dignity Methodist Family Medicine Residency Program. For food chemistry-wise, my undergraduate degree was in biotechnology at the University of Wisconsin, River Falls, where I was involved with the Ag Biotech Lab for several years.
And what are your pronouns?
He is fine.
Thanks. Zach, would you introduce yourself, please?
Hi.
Real loud.
Yeah, you
Hi.
really got to give that microphone something.
Hi, I'm Zack.
And what's your cred for knowing about food chemistry? I mean, that's approximately my cred as well. My name is Rachel. I consider myself a kitchen nerd of the highest caliber, and that includes knowing how my food actually turns from ingredients into meals.
And hi, my name is Renee Petersen, and I am a teacher, licensed Minnesota teacher. I have a string of licenses, I have a string of degrees, blah, 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 poverty level pay, yada, yada, yada.
You already said you were a teacher.
Yeah. I also do living history. I've been doing living history for about 35 years. And my focus in the living history is food and the food material culture. I also recently, actually last June, I published my first cookbook on the Viking food shed.
That's really cool.
Yeah,
I'll ask you to plug that again later with like a link.
Okay, well I have all that stuff. But I also do a lot of herbalism and using things that I pick in the wild, like foraging. I can turn that into food, I can turn that into medicine, and there's a huge difference between tincture and tisane. So if you add water or if you add alcohol to something in order to get something out of it, that's an entirely different thing. And there's some of the food ways and social norms that we have around certain foods and certain ingredients. I've done extensive research into that, and I do have a bibliography available if you so desire.
So Renee, how about you get started talking about that whole water and alcohol business? And we do have one more seat in the front row. If someone wants to take it.
We got one spot. Yeah.
All right, we gotta
really
take it.
have to ask nice though if you really want me to bite you. How many people here drink tea? All right. Now you know that tea actually is a plant, Melaleuca, right? It's a plant.
Melia sinensis.
Oh yeah, I always get the Latin names wrong. I know common names, not Latin names. But if I were to take hyssop and dandelion flowers and a little bit of calendula, that's not tea. That is a tincture. If I tincture, and if I put those herbs into cold water, different things extract. If I put them into water that has boiled and you have taken it off the boil, that will extract certain things from those plants. If I put those plants into boiling water and I cook them into the boiling water, that also excuse me, that also extracts certain elements. You're looking at the esters, the natural alcohols from the plant, and you're also looking at the oils from the plant. Adding heat to anything is a super game changer. Heat is an element of change, and keeping that in mind when you're working with your food, that's really important.
So, what's happening when you put your herbs into water? Like, what's the chemical process?
If you're putting your herbs into, or whatever plants you're using, if you put them into cool water and you just let them steep, which is a fancy word for soak, you just let them steep and then you strain out the solids and you have a liquid, you will have a nice flavoring. If you have an upset tummy, if you take barley and you put barley into room temperature water and just put a lid on it and let it sit there for about 2-3 hours, strain it out, and if you drink the barley water, it will help soothe because there's not a lot of heat that's involved, and it will help pull out some of the emollients that are in there.
Emollients.
There you go.
Yeah, emollients.
What are emollients?
Chemistry. So, I'll hop in here.
Absolutely.
Now, so what we used a whole lot of words.
We used
There's a lot of words in there, and I'll start explaining kind of what some of those words are and what we mean with some of those words. We're going to go back to water, right? When we're seeping anything, we have water. Water is a molecule that is composed of 1 oxygen and 2 hydrogens.
It says on one of those posters outside.
Yep.
Dihydrogen monoxide.
Dihydrogen monoxide as a chemical term. Now, because water is composed of an oxygen and 2 hydrogens, it has certain properties. And one of those properties is that other molecules with lots of hydrogen and oxygen in it like to sit in between the various molecules of water. So, there are molecules, however, that don't have a lot of hydrogen and oxygen in ways that like to sit in between the molecules of water. And every substance, every chemical, will float and will get absorbed by and mix with these molecules at a certain extent. That is the term that we call solubility. How much does something exist in the water itself? Now, let's say we don't use water. Let's say we use vegetable oil, for example. There are substances that do much better and can fit in between the various molecules of vegetable oil than can water, and vice versa. Now, you don't have to have a substance that will be one or the other. it can dissolve somewhat in water and somewhat in vegetable oil. That term is partial solubility. And when we start dealing with heat, for that changes how much of these substances can be dissolved in the water. I'm going to use water for these examples, what we use with the most. I don't know too many people here are going in boiling vegetable oil, so we'll just stick with water.
When I do garlic oil, I absolutely
When we
boil
do,
vegetable
yes,
oil.
Add them into it.
that is another great issue for dealing with solubilities. And what do we want to get out of our various starting materials like garlic or dandelions or whatever?
What about using whey, whey protein? Because you not only have water, but if you have whey, and when you open up your yogurt and there's that liquid that's in there, don't throw that out, put that in another jar. That's whey. That's really a useful thing. You can use that, and it has a little bit of an active culture in it, and that will help pull some things out, because ultimately what you want to do, right, is break down some of the cell walls to get more of that stuff out.
That's fermentation process.
Yep.
You're actually fermenting. We'll talk about what fermenting is technically.
Yeah.
I think here in a second. Dealing with, we'll go back to solubility.
Same topic, so we can go back and forth.
We can go back and forth? Okay,
Yep.
so
Yeah, 'cause we-
I'll wrap up with discussing solubility, which is, you do.
See, I wrote it down because brain.
So
Pull it back up too.
one of the physical principles of solubility is that it changes based on temperature. So how soluble something is in water is going to be dependent on the temperature of the water. You may get everything out of a bag of tea leaves if you dump it into cold water than if you do in hot water eventually. But time is a factor on all of this. You have something that is dissolvable in water. You have something that it's coming out of. The term that we use for that is extraction. So the chemical term is you are doing an extraction. You have an extract of, say, caffeine, or the various chemicals that make up garlic flavor. You are creating an extract. And that process of extraction is dependent on several chemical and physical properties. One, the temperature of whatever you happen to be dissolving it in. We call that the solute, S-O-L-U-T-E. One is whatever you happen to be, the chemical, the partial solubility, what you're trying to get in the water. Another issue is the temperature, as you mentioned, how hot it is. For the most part, the higher temperature that your solution is, the more you're going to be able to get out of it, and the faster you'll be able to get out of it. And another issue is the particle size of that in which you're trying to get out.
And if you want to keep some of those larger particles or some of those more trapped particles from getting into your solution, that's when you do cold brew coffee, cold press coffee, or that's when you do sun tea, where you do let it do that cold steeping that whole time.
With the cool thing about cold brew coffee is if you don't add the heat, you don't get the oil from the bean.
Yeah, so
Oils anyways, yeah.
oils. So going back to partial solubility, we think about fats as like our butters and our margarines, vegetable oil and engine oil, and stuff that if you put a drop of it in water does not mix very well with the oil. But there are a lot of oils and fats that are in our foods which are partially soluble in water. Part of the molecule does just fine in water, the other part of it does not, and because of that difference, only some gets into the water, very small portions. And that can change with things like heat.
And how much heat or how long you have heat.
Yeah, so when we're dealing with our partial solubilities and we're doing these extracts and we're dealing with something like coffee or tea, let's say we get some of those oils into the water, and then we deal with the other properties of heat and solutions, which is oxidation. People have heard that term before? Yep, oxidation, good.
Let's save oxidation for a few minutes from now and jump over to fermentation quick.
Fermentation, okay.
Yeah.
Oh,
What's your favorite fermented food? Zach, what's your favorite fermented food?
Would cheese count?
Absolutely.
Yes, absolutely.
Cheese is fermented.
Lactobacillus.
I'm a fan of dill pickles myself.
Now, are dill pickles, is that a pickling process or is that an active fermentation? Because
It depends on how you do it.
You can do it as a fermentation, or you can do it in brine, or you can do it in vinegar.
Or you can do it in whey. No, I'm not. I was
Salt,
seriously
yeah,
not
that's
kidding. There's a huge amount of research that says that you can do pickles in whey, and I'm currently trying an experiment right now with parsnips and carrots at home in a whey mixture to see what it does, and I'm going to leave them in there for several months before I open it, as an exercise in how long, because it's a food preservation tactic.
let's define
Yeah, let's
fermentation.
define
Yeah,
What is
that should be good.
fermentation? That's a good thing. Fermentation is a biological process. So it's not a biological process which does chemical changes. So there's typically some sort of microbe, be it a bacteria or a yeast, which are usually the ones which are used for fermentation. And those bacteria or yeast use whatever you give them, be it whey or milk or sugar or vegetables, what have you, and they go and they live off that. They grow. They use that as energy, mostly. Whatever is left over then goes and changes the food that we like to eat. For example, kimchi, sauerkraut.
Oh, have you ever had kimchi made by the little Vietnamese grandmas? Okay, the kimchi that you buy in the stores in a jar.
Vietnamese or Korean?
I've had both.
Okay.
The stuff that's in the jar in the stores is a picture of kimchi. So if you ever get invited to have Grandma's recipe kimchi, your answer is yes, please. You're going to pause long enough to take the breath. Because Grandma made kimchi is spicy, but it's also fizzy, and it's crunchy, and the flavor profile is
Complex because of all those bacteria and their byproducts.
Yeah,
yes.
You're eating the byproducts of bacterial fermentation, which is usually acid, right? That's why it's tangy. Fizzy would be dissolved carbon dioxide. The same reason that fermented beverages are fizzy is that the yeast or bacteria, depending on the beverage, grows and it respires. It uses whatever oxygen is left there and turns into carbon dioxide, and that dissolves just like our oils and substances in there, and then we pop the cap, it goes and fizz.
I do have a question for the audience. How many of you folks have made your own sodas? Made your own soda? Not with a soda stream, but actually make your own. Because my grandfather kind of thumbed his nose with the whole prohibition thing. And not only did he make wine, but he also, when we were kids, he made some really excellent root beer. And
That's sarsaparilla.
oh man! And they were using, at that point in time, hi, my name is Renee and I'm in my 50s. So the sugar profile, the sweetness profile of sugar in the 70s was a little bit different than I think what we experience today because of the processing. But in making your own sodas, you throw some yeast in there and you let it go on the counter for like 2.5, maybe 3 days because you want the fizz, but you don't necessarily want the alcohol. And homemade ginger ale is so... Oh, I see people back there. Yeah, homemade ginger ale. Ooh.
Because you don't have to let the bacteria eat enough sugar to turn it all into alcohol.
You just want it fizzy and fun. So, and I absolutely recommend making your own sodas. Absolutely. Because that high fructose corn syrup, I'm going to get on my box here for just a moment. High fructose corn syrup is
15
killing
seconds
people.
on your box, and then we need to move on.
Right there. High fructose corn syrup is going to kill you, so stop eating it. Okay, I'm done.
All right. So let's talk about yeast. Let's move on to baking. This is,
Good segue,
yeah.
Yeah,
So
that's a good
who's
segue.
got a sourdough starter? Yeah, so that is a living bacteria. That's that fermentation that Kurt's talking about. You have to actively feed it. You have to let it produce its carbon dioxide. And carbon dioxide is those little bubbles that show up in your bread. I have a friend who actually has a very hard time with yeast bread because she looks at the yeast and says, it's a living thing. I can't possibly just put it in my food so I can kill it and eat it. It's like, you do eat meat.
So that is a fermentation as well, to an extent. And sourdough is like one of the United States' sole culinary contributions to the world. Sourdough bread, yeah. And I'm sure
We're
there's a
talking
history of that
native
one,
corn
too.
is actually a...
That's more south of us.
Well, from the Americas in general, I read a book, and I totally forgot the author. He wrote a series of books, but the first one they wrote is something called Indian Givers. And this book was written in, yeah, it's kind of an offensive name, but he wrote it in I think it was the 80s. And it talked about the contribution of Native Americans to the world table. And for the remainder of this session, I'm going to refer to what we call corn in this country. I'm going to refer to it as maize, which is its true name. It is not corn. Corn, C-O-R-N, what we're used to using, is actually a late Middle English generic term for grain, for ears of grain, ears of corn. So when you say, yeah, we got corn, my brain is automatically going to go, wow, you got barley? Because that was one of the most common grains in that time period. But when I talk about that, it's maize.
Sure.
And the native folks, some archaeologists were excavating in Central America, and they were finding these stepped terraces all the way up this mountain. And they started to figure out that this was bioengineering. At the height of the Aztec and Inca Empire, there were something like 6,000 varieties of maize that were grown in different altitudes, with different moisture contents, different usage.
But that's a good topic as far as food chemistry as well, too.
Yep.
Because let's say we take our maize and we grind it up. Can we eat that right away?
No,
That
not
depends-
nixtamalizing it.
There we go.
Yeah,
That's the big name that I'm looking for.
Yeah, so nixtamalizing is a process, and I'm not entirely sure what the process is, but you use lye to,
Yeah.
I
Sodium hydroxide.
yeah, and I'm ashamed to not know the actual chemical thing that the lye does to the corn.
Hydrolyzes.
Hydrolyzes. What is hydrolyzing, Kurt?
Hydrolyzes is when you take the starch, which are great big long chains of things. Well, everybody's got a pretty good idea what starch is, right? It's what makes up our bread and potatoes, those types of compounds. Those are great big long chains. And if you get them long enough and you make them into branches, as plants have a tendency to do when they're making, because it's a storage compound for plants. That's how it stores its energy, as a starch usually in the roots. So you take that, you can't eat it. Our bodies, our stomachs, our digestive enzymes can't break apart those great big long branched chains of starches too well. If you've ever heard the word insoluble fiber, you get an idea of what you're talking about. Roughage. However, if you go and you take sodium hydroxide and you mix it with water and heat and put this starch in it, chemically it starts breaking it apart. Not all of it, obviously, it doesn't turn it all into simple sugar, but it breaks it apart enough that now we can eat it. It chops it up chemically like a molecular cleaver and breaks it into itty bitty pieces, which now we can then go and eat.
We will take questions when we are done with the talk. Yeah.
Yeah, please write them down. I don't know if you need a notebook.
We got some pads up
I
here.
got some pads up here.
Forget.
And I got
So you
writing
don't,
utensils.
yeah, you don't have to grind the corn up before you nixtamalize it. That's how you get hominy.
Yep.
Hominy is just nixtamalized maize.
And polenta. Think about polenta.
Mhm.
Makes sense. But that's chemistry.
Mhm.
That's how that works. Fermentation, getting back to that topic.
Oh, I just wanted to add a quick thing. is that if you have a whole grain, in order for maximum
Nixtamalize.
I have a hard time with that one. You smash it up super fine, and if you need to break it down, your wood ash left over from your cooking fire, your wood ash, just put a little spoon of that in. I cook with fire all the time. And you mix that up, gives it a nice smoky flavor, and it helps break down those big long chains, and it makes it nice and soft. And as the first part, if you were to take, if you had a maize sponge, and by sponge, I don't mean the thing that you wash your dishes with or cake. I mean, it's a living sourdough piece. And if you have a maize sponge, and you add it to this maize flour and your spoon of wood ash, you now have a nice sort of living kind of bread. It's not going to rise anything like what we're used to, because the gluten that's contained in corn is an entirely different gluten that is in wheat, rye, and barley.
So you're talking about?
We moved into baking.
We moved into baking. Let's talk about baking then, because you talked about gluten.
Mm-hmm.
Right, let's discuss gluten and either the benefits or evils thereof.
So what Renee was talking about with the gluten that's in wheat, rye, and barley, that's a protein. And one of the, do you bake, Zack? I can't remember if you said you bake or you cook.
I've done some baking.
Okay, so like when you're kneading bread, that's to help the gluten form longer chains. So, are you familiar with this or no?
Kind of.
Okay, so I'll keep talking about it. So you're forming these long chains of gluten, and that's how you get that nice stretchy property of bread.
So that when you're kneading the bread, depending on what kind of flour, if you're using wheat flour, that's got some of the highest amount of gluten in it. What you're looking for is you're looking for the ability to stretch it thin enough for you to be able to kind of see through it. Not perfectly like a window pane, but you should be able to see
And
fairly
powder
sharp,
baking holes.
light baking, or light, a little bit of light, sorry.
Translucent?
Yeah, that's the word.
So what chemically happening is what's going on there. We talk about gluten as a single thing. Gluten is not a single thing.
It is not.
When we're thinking about wheat gluten, those are actually two separate proteins. And they don't do anything when they're dry. You need to add water to them. However, when these two proteins get in contact with water and are mixed, then they start coming together and forming long chains. And the more you mix them, the longer they get. From a physical chemistry side, when we're dealing with things, this is polymerization. We are polymerizing these various, what we call subunits, which are these repeated sequences of these two protein molecules. The stiffness, the elasticity, has to do with the amount of what we call cross-linking in between those two molecules. You can imagine long chains, like spaghetti. And now take that spaghetti and you go across and you clamp two of them together. That's a cross-link. And as you get these long chains and you move them and they develop and they start tangling amongst themselves, that gives it the physical properties that we associate with breads. The elasticity, the rise of it. Now,
So are we looking at a tangle of Christmas lights or a bundle of firewood?
Christmas lights. More Christmas lights, not fire. That's pretty rigid.
Yeah.
Now, one of the nice things that has, and getting back to that great big word, colligative properties,
Thank you.
is that you can put stuff inside of these tangles, like starches. And other things, going back to fermentation, like air bubbles. If you wind up having yeast in that mix,
Yes, and that's where that carbon dioxide goes.
Now you remember that elasticity we were just talking about? What that elasticity does is you get the bubble making with the yeast, you get the bubble making there. The elasticity in the dough that you have kneaded and you've made those chains stick together, when you have the bubbles there and you bake it and you kill the yeast, the elasticity is what holds the space. So basically it's kind of, my brain keeps going to coral. That it's like you've got the map of where all the bubbles were, and the living part that was making the bubbles has been baked away. We have suitably killed all of that living stuff, and we've got the hollow spaces where they were.
The heat of baking has gone and chemically changed the starch structure.
Solidified it.
And it has gone and bound it all together, so it's no longer squishy. And it has removed all of the water, so there's that elasticity that was left doesn't exist anymore. And now you're left with a more rigid structure.
Like a coral.
Like a coral, which is a different biological property.
Very.
So there are a couple of things that we can do to modify chemically when we're talking about bread yeast. And if you ever take a look at the back of your package of bread, commercially available bread, and you look at the ingredients, it's usually things like, wheat flour, water, salt, yeast, and then a bunch of different chemical names that you may or may not be able to pronounce. Yeah, they do certain things. The individuals working at the bakeries, they have a lot of PhD level degrees and knowing what's going on. It's a very complicated process, but they're using those chemicals, some of them at least, to modify the elasticity of the developed glue so that it is more or less consistent. When you're making a batch of bread at home, for example, it's sitting there, you've got a loaf of about this big, and you are fermenting it. One of the things that fermentation does is produces heat. Think about that. Now imagine you're an ant, right, and the size of a bowl and how much they're. Now take that, scale it up to human size, and you have an idea of how much heat this thing produces when you're trying to ferment, several hundred tons of bread. So at an industrial scale, we worry about that, and we need to make it consistent. So by modifying, say, the pH, by adjusting and maintaining the pH balance across these various gluten chains, the acidity levels, we can make it more consistent.
I used to work at the Tasty Bread Factory. Yeah, the celiac girl worked at the bread factory. And when he says tons, he's really, really not kidding. They mix the bread in a trough that is it's a little bit longer than this row of chairs, and it's in a V sort of format. The top of the V is as wide as 2 rows. And there's this giant auger in the middle. And when you say that they have sacks of flour, and we think of a sack of flour,
Oh no, like 50-pound sacks.
Yeah, they're like massive quantities of flour, and for the most part, they have these big hoppers that have a cloth tube at the bottom, and then they put the trough underneath it, and it's on a scale, and everything is done by weight, including when they add the honey. That's weight. And it's absolutely amazing to watch these giant things go.
From a chemical perspective, doing something at a small scale, whether it's making tea or coffee or fermenting bread or doing all the other experiments that we have to do at home that winds up our cooking. Trying to do it at scale, at industrial scale, you get individuals with a lot of math gets involved really quick.
Oh yes. Try cooking for 75.
Yeah, not even just cooking scales, but we deal with thermodynamics of cooking. We deal with physical properties that you may not have to consider if you're using a standard cooktop kettle, for example. If your kettle holds 50,000 gallons, then you have to consider things like what's the temperature in the center of the kettle, versus the temperature on the outside. Where's your heating elements at? You can do this at a small scale. If you've ever cooked on with a big kettle at home and you've seen different stuff rise to the top, if you've boiled sugar and you see sugar crystallizes around the edges, then you're dealing with an issue of solubility. And that becomes very difficult at scales. So a lot of people get involved with a lot smarter things than I am in order to sort those problems out.
So let's talk about heat.
Heat is
Let's
good.
talk about what heat does, because heat can do a lot of different things. It can boil off all the water in our bread. It can solidify these proteins. It can cause, I know someone in our chat mentioned Maillard reactions, which there are several.
Which are not ducks.
No, they are not.
Not duck
And
reactions.
there are several kinds of them. So I want to start talking about caramelization, which is specifically for sugars.
Yep.
So if you have sugars in your food, and there are sugars in plenty of foods, even though they don't say sugar on them, you can caramelize that sugar by putting heat on it. It literally changes the structure of the sugar so that it turns brown and has a more buttery, nutty flavor to it.
Like in the Great British Bake Off. Did anybody watch that show?
Okay.
Yeah. Right. So when you see them in the big tent, and they have the convection cooktop, and they just dump some sugar into this pan, and that's all they do, and they wait for it to start melting, and you get to that caramelization point where you're starting to get the color on it. There's some big changes that are happening there.
Let's talk a bit on the chemical side of things. What's going on? Sugar is a hydrocarbon. And what that means is it's composed almost entirely of the molecules of hydrogen and carbon. The sugars that we think about are a chain of those carbons that are linked together and then made into a circle. So it's not a circle, it's a hexagram or a pentagram for the most part when we're thinking about sugars. But that's how we think about a sugar. When we apply heat to that sugar, then we get back into, again, the big word of hydrolysis, which is breaking it apart. So it's no longer a circle. Now that circle is now a straight chain. Now it's more like the starch that we're used to dealing with in our potatoes and breads. And we can start adding more heat to that. Now when we start adding more heat, maybe then we go and knock off some of those hydrogens, right? Now we break it apart. Or that then goes and changes chemically and starts combining with other molecules that may happen to be hanging out. So, yeah, kind of. Yeah, it's a little bit more than that, but yeah, we'll go with that. So, that'll go, and that is what we call our caramelization. So when you add heat to things, usually they break up into smaller bits for the purposes of cooking. And then we mentioned something called Maillard reactions. Maillard, which is caramelization is kind of, it's the same thing. There are a whole class and series of reactions which happen specifically to proteins. And proteins are in a lot of foods that you don't think about, right? If it comes from a living thing, it's probably got some amount of protein in it, however small.
Even plants, it's got a protein in it because plants need protein themselves.
Mm-hmm.
They just need to have it in lower quantities than omnivores or carnivores would need.
So like, yes, legumes have a higher quantity of proteins than other plants, but all plants are going to have them.
Yeah.
So let's say you are a meat-eating individual, and you particularly enjoy the flavor that you get when you take a piece of steak and you put it on a hot grill or what have you. What you're doing there is you're applying heat, and those various proteins are breaking apart and rearranging themselves and forming chemical bonds, actually changing the structure of the chemical protein itself, and forming different structures. And they follow kind of basic rules, but the idea is that you break apart, you form these molecules, it's no longer part of meat. They've broken them all. The meat bits that make up the meat are no longer there. They're now kind of free-floating. And they form different structures. And those different structures taste different, depending on your preference, good or bad, or somewhere in between. So the whole class of what we call browning, if you put a piece of meat or a piece of anything, that's why the starches on your bread, when you put it in the oven, you get brown. It's that classification of Maillard reactions, of browning reactions that occur.
And it's going to be a different Maillard reaction if you decide to boil or pressure cook your meat than if you're searing it to get that browning. Just because of the wet heat versus the dry heat, it's a different way that it reacts.
The presence of water in the heat takes the place of other chemicals. And that's a process when we're doing more organic chemistry, where if you have water that's in there, it'll take its place and it'll break it apart. If you don't, then maybe proteins come together instead of breaking apart, and that's where we get our browning reactions.
One thing I think that we should also think about is every step that you take with a piece of food from its harvest to your mouth can and does reduce its nutritional value.
Sometimes it makes it more bioavailable, like nixtamalization will make the nutrients in maize more bioavailable to you.
Fermentation will increase nutritional
But
value.
If we want to get to that, we have got to,
You gotta hustle.
yeah.
Okay.
Yeah.
Hustling.
So if we want to move on to biochemistry, we can do that.
Okay.
Can we talk about amylase?
Yeah, we can talk about amylase.
Yeah.
We talked
amylase.
about heat breaking down starches, but obviously our bodies don't produce that they don't get that hot, right? We're not boiling in our own skins, despite the fact that it may be summertime.
If we go over 98.6 Fahrenheit, we're in trouble.
No, that kills me for menopause then.
We're in trouble. So there are other ways that our body deals with sugars, and there are other ways that we can go and break apart the starches chemically, and reasons why we do it for cooking, with a substance called amylase, which is an enzyme. An enzyme is some sort of protein which goes and it changes things from one thing to another. And amylase is a substance which changes starches into smaller sugars. So what's a good example of a substance that is produced by amylase?
Well, amylase is in your mouth. Did you know that?
You make it.
Yep. It's part of, in the human digestive tract, amylase is in our mouth. And technically, it's not technically venomous, but because we produce this amylase in our mouth, if we bite, like if I come up to you and just bite you and break the skin, you would need faster treatment for that if you got a bite from me as opposed to my dog. The dogs don't have as much or a similar amylase in their mouth than we do. And it will begin, because that's what the action of chewing and the amylase in your mouth start. It starts the digestive process. For humans, our digestive process with a head. So amylase starts to, between the chewing, the mastication, and the amylase in our spit, we begin the breakdown and digestion process. Now remember, once it gets down to the stomach, you've got the hydrochloric acid that's in there, and that will further break it down into its molecular? There you go, that's the word I was looking for. Breaking it down into its molecular pieces, so that then we can start to have those bits of energy and bits of molecules moving throughout our... I am just losing my brain.
You'll start breaking it down so you absorb it and use the rest of your body. Again, amylase goes in, hydrolyzes things. That's breaking down. The other bits is, let's say you've gone through all this cooking process and you've made delicious brown bits, either on your bread or on your meat. And we get into, I'm tasting. What is flavor? Flavor is a cellular response. You have a receptor on your tongue. Or a receptor, you have a lot of them, However, how many people have seen the little taste maps where you get the picture of the tongue and it says this is the part that has a, yeah, toss that out of your brain, that's bad. That is completely garbage. It has nothing to do with that. Everything, all the
Taste
taste.
everything everywhere.
Yeah, it's all over the place. And you have these little taste buds. Everybody's heard of taste buds, right? Right? They're little bits that stick out of your tongue, and they are coated with nerve cells. And these nerve cells end in a little tiny bit that goes out there, and it wants to latch on to some sort of chemical molecule. All flavors are various chemicals.
Including bad ones.
Including that
Yep,
one.
that's why
That's why you have flavor. Taste to begin with.
Yeah, so that we don't eat rotten, poisonous food.
Yeah, and that's why the nose and the scent and the taste receptors are where they're at. I always sniff what I eat because I've been sick before, and I don't really want to do that again because that was
They have a badger room for that now.
bad. Yeah, I understand badger for that. I'm a survivor. So.
If I see them, I'll tell them to come to our panel tomorrow and give you one.
Oh,
Saturday or whatever it is.
absolutely. I'm a survivor.
So,
Tummy troubles.
yeah, so when you think something is hot, and in the terms of spicy, that's because there's capsaicin or another, I'm not sure what the numbing spice
There-
chemical is.
What's the one that's in mustard? It's not capsaicin.
No, but there's these
What
series.
did you say?
Pepperin?
Yeah, that's the one that's in mustard and horseradish, and where you would get the zippiness in northern climate foods that can't support capsaicin producing plants.
And that's why my mom can do horseradish, but not capsaicin.
Here's a fun fact about capsaicin. How many people enjoy spicy food? Yeah, I got something to tell you all. You all enjoy pain.
Yes, in fact, I do.
The capsaicin, the receptor, the actual chemical portion, which it's called I won't say the actual name of the receptor. It's a pain receptor. It gets pain. What does it respond to? Damage, cellular heat. That's why it's hot. It's spicy. It triggers for a number of different reasons. One of them is thermal damage. So it's like, this tastes delicious. It tastes like pain. You bunch of sickos.
Yes.
And that's the way you interpret that sort of sensation. Is that chemical, that what you've just gone and released from spicy peppers, which by the way, birds don't. They don't have that receptor. Which
Someone
is
get the door, please.
the thought of why they think capsaicin developed in the first place is so that these plants wanted birds to spread their seeds and not mammals. So they developed this thing because birds have no problem with it. Mammals will say, this tastes like pain. I don't want to do that until you get to us with something that says, no, I want this. I want that pain. So what that happens is that chemical receptor triggers and a bunch of things it's one of those little diagrams where the marble goes down the chain and it hits this and the wheel spins and all that. That's what happens. It eventually goes up to your brain and it says, this tastes different. And for some people it's like, yes, more please. And then you make hot sauce. And for some people it's like, ew, no, I don't want that at all. So that's kind of how flavors work. It's just chemicals.
The difference between jalapenos in your food and pepper spray.
Yeah, it's the amount. It's a dosage issue.
You know what's really hilarious? I've always thought this was really funny. In making mustard or horseradish sauce, and I want you to say that 10 times really fast.
Horseradish sauce.
See? Blah, blah, blah. When you're making it, if you put your mustard seed into the freezer and you put your horseradish root, don't grate it yet, in the freezer, and you put your cider vinegar in the freezer, you don't want the vinegar to freeze, you just want it really cold. The colder your ingredients are when you mix them together, the hotter your horseradish sauce or your mustard gets. And I don't understand it precisely why it's cold.
Solubilities.
I'll have to
The
try that
cold?
for Passover this year.
And it has to do with, we get in a whole lot of details as far as extraction and the chemical process, what goes into extracting something. Why do you grind your beans when you make coffee? Because the smaller the bits and pieces are, the more stuff you get out of it.
Area you have.
What happens when you freeze a plant? Well, the water crystals solidify and it breaks open all those cells. So you stick a fruit, a grape in the freezer, by the time you bring it off and thaw it out, it's mush because all that cell structure is done.
But
However,
blueberries are also sweeter.
yeah, because things happen, chemistry happens, and it goes in and changes all that. So that's stuff that happens on a chemical basis through a physical state change. You're instead of grinding it up, you're letting frozen water do the action for you and then extracting it.
Yeah, because after I take the mustard seeds, I'll take them out of the freezer and then I will grind them. And as far as the horseradish root goes, when the whole thing is very cold to the touch, but not frozen, that's when I grate the horseradish root.
So let's take questions. We've got about 10 minutes left. What chemical food questions do you have for us? Go ahead.
So, some people think cilantro tastes like soap, and it's like genetic and stuff like that. So, did some people, I guess, evolve to think that should be used or like avoided, or?
So the question is that some people think that cilantro tastes like soap. Why? And there's actually a little interesting genetic thing here. So I got some fun genetic testing done, and one of the things that they looked at was the gene for does cilantro taste like soap? And on me, it said you should think cilantro tastes like soap. But in their explanation, they said, but if you come from a culture where cilantro is in everything, you probably don't notice it anymore.
Going back to receptors, this is more molecular biology than it is chemistry, but the function of any sort of protein has to do with the shape of it. And in individuals that think cilantro tastes like soap, there is a mutation. There's a difference in the actual genetic code that makes that receptor protein. And that changes the shape of it. And the changed shape means it doesn't respond to that chemical as the way that it would. It doesn't bind it is the word that we use, right? It doesn't connect with it, and because it doesn't connect with it, it doesn't start the little marble down the chain to do the things that somebody with a different shaped receptor would do with the cilantro molecule. And that isn't an evolutionary advantage or disadvantage because nobody survives entirely off of cilantro plants. I hope.
Really?
Yeah. Believe it or not.
Especially not the cilantro that's still in my fridge.
So that's what's
biochemistry
happening.
right there.
Yes.
Agriculture.
But if you are, for example, in a culture where there may be a genetic change based on your diet, and I'm thinking particularly of lactose tolerance from cultures in Southeast Asia, if they don't have a large portion of their diet, they actually have different genetic changes for lactose, handling lactose.
I mean, the majority of mammals turn off their lactose tolerance after babyhood.
Yeah.
But
Yeah, usually about 11, 12 years old when you go through the change between being a child, and that's, get the terrible twos, and then you get that time in middle school where's your brain, kid? Well, that's because it's under construction.
yeah.
It's serious. It's under some major construction.
That's a different chemistry.
Yeah, that's an entirely different chemistry.
Yeah.
But that's the point in time where if your body is going to shut off the ability to process casein, that's when it's going to happen. That's when you're going to start to have the struggles. Those are going to start to show up at that time.
Typically, there's people who
Typically,
have it
yeah.
later onset for various reasons.
Isn't casein different than lactose though? Like
Yes,
Oh, yeah.
casein is a protein.
Okay.
And I said
Lactose is
the
a
wrong
sugar.
thing.
Yeah.
I said the wrong thing.
But generally, for those of us who have dairy issues, if something has one, it probably has the other, and I don't want to eat that. Do we have any other
Unless it's
questions?
fermented.
No, even if it's fermented.
Ah,
Orange.
Octothorpe.
Yep.
what do you have to say about science, or in regards to science or chemistry or food, about foods that are bad for you, like KC toxins or like ethylene glycol, like actual poison? Why does it taste not like poison?
What do you have to say about actual poisons that don't taste like poison? Are you thinking like antifreeze?
Yes.
Ethylene glycol. Yeah. So the toxicity is in the dose, and the flavor of it, whatever your receptors bind to, has nothing to do with what happens to it after it gets past the receptor. It's there to help you out, but for the most part, if something is going to cause you problems, it doesn't necessarily have to do with how it tastes. So in some cases, for the case of ethylene glycol, it will trigger the sugar receptor, the sweetness receptor, but it causes other problems downstream.
And human beings are hardwired to want sweet, to want fatty, to want salty and acid. We are hardwired for this. This is why all those fast food places can get away with serving you plastic, because that's literally what a lot of that stuff is. It's not considered in other countries in the world. What fast food places are serving you is not technically food, like high fructose corn syrup, all the rest of that, not technically food. And as it goes through your system, you can either have the really horrible reactions with the hydrochloric acid in your stomach, or incompatibility in how your body can and will absorb certain things. You have problems with that, and that's the reason why if you spend a lot of time eating the fast food, your body has no idea what to do with this, and it goes,
And then you get the tummy ache survivor ribbon.
Yeah, and then you get the tummy ache survivor ribbon, or you get bigger thighs. Because I don't know what to do with this. We're gonna make some fat.
Yeah.
Go ahead, Green.
That raises an interesting question about, you mentioned some things that you can eat and not immediately fall over from. So what is the definition of food?
So what is the definition of food? Because there are things that we can eat and not fall over from, but not great.
I would say it's probably anything that you can consume that has some level of nutritional benefit that you can reuse in the rest of your body. So is water a food? That's a good question. It doesn't have nutrition in and of itself, however, you need it for continued survival. Salt, is salt a food? Well, you need salt, but it's also not nutritive.
Yeah.
So I think I would probably define a food as anything that you would need to consume that gives some sort of benefit for continued survival, for nutrition, or for continued function biologically.
Because when you eat a lot of salad, because I'm trying to reduce, because I did not attain this size eating trash, I can tell you that. I'm really good at cooking, and so
and that's a genetics thing too.
Yeah.
How much insulin your body likes to produce and store, and how quickly you build up a resistance to it.
Yeah. So if I were to sit down and consume my daily 2,000 calories worth of solid raw plant material, that's like a bale of spinach. Now, while I like spinach just fine, I like to have some other things with it, like tomatoes and mozzarella cheese and balsamic vinegar. But if I were to eat that bale of spinach, I would get some vitamin C, some vitamins, some minerals, but a majority of that is going to be fiber.
So you wanted to plug Renee. We're at time here.
We're at time, okay. So, hi, my name is Renee Petersen, and I wrote a book, Modern Urban Viking Cooking. I do have a couple with me. I do have my business cards up here, and I have badge ribbons because